March 24, 1945. Xanten, Germany. British Royal Engineers stand at the Rhine River's edge watching retreating German forces blow the last bridge connecting them to Allied advancement. The explosion sends 400 tons of steel into the river. German commanders are celebrating. They've just bought themselves weeks, maybe months. Rebuilding a bridge across the Rhine requires massive cranes, specialized steel fabrication, concrete pouring that takes 30 days to cure. Except 31 hours later, British tanks are rolling across a fully operational 200-foot bridge at the exact spot where twisted wreckage sits underwater. American observers watching through binoculars radio back, "Impossible. The bridge wasn't there yesterday morning." But it was. Built by 60 Royal Engineers using prefabricated panels that arrived on trucks, assembled by hand without a single crane, and strong enough to carry 40-ton tanks. This wasn't magic, this was the Bailey Bridge, and it was the reason Germany lost the logistics war before they lost the shooting war. When Donald Bailey sketched this design on an envelope during his train commute in 1940, he wasn't trying to win the war. He was just solving an irritating engineering problem. Why did temporary bridges require cranes when panels could interlock like giant Lego? That simple question, asked by a shy engineer nobody had heard of, would build 700 bridges in 48 hours during D-Day and keep Allied armies advancing when Nazi strategy assumed blown bridges would stop them cold. Before we reveal how one envelope sketch changed military engineering forever, smash that subscribe button. Like and comment which WWII innovation amazes you most. This channel exposes the quiet genius that actually won wars. Now let me show you why Field Marshal Montgomery called this the weapon that defeated Hitler. September 1940. Donald Coleman Bailey sits on the 7:42 morning train from Rotherham to Sheffield, watching the British countryside roll past. He's a 42-year-old civil engineer working for the Ministry of Supply's experimental bridging establishment. Quiet, methodical, the kind of man colleagues describe as competent but unremarkable. He's spent 20 years designing permanent bridges, concrete spans over rivers, steel structures supporting highways. Nothing innovative, just solid engineering that does its job. But Britain is at war now, and the war is creating problems Bailey's permanent bridges can't solve. The previous night, he'd attended a briefing where military officers described the disaster unfolding in France. The German blitzkrieg isn't just about tanks and aircraft, it's about speed. German forces advance 50 miles per day, and when Allied forces try to slow them by destroying bridges, the Germans simply build new ones overnight using specialized bridging equipment. British forces have nothing comparable. Standard military bridging doctrine in 1940 involves massive steel trusses transported on specialized vehicles, assembled by crane, requiring engineering companies with weeks of training. A typical temporary military bridge takes 3 days to construct under ideal conditions. Under combat conditions, a week or more. The Germans are crossing rivers faster than the British can destroy the crossings. Bailey pulls out a notebook and starts sketching. He's thinking about a children's toy he'd seen recently. An erector set, metal pieces that snap together with simple connections. What if a bridge worked the same way? Not a single massive structure requiring cranes, but small identical panels that soldiers could carry by hand and connect like building blocks. The core concept crystallizes quickly. Each panel would be 10 feet long, 5 feet high, made from welded steel creating a rigid rectangular frame with diagonal cross-bracing. Weight needed to be manageable, maybe 570 pounds, light enough that 4 men could lift it. The panels wouldn't bolt together. Instead, they'd use steel pins dropped through aligned holes. No tools required beyond a hammer to drive pins. But the revolutionary insight is how the panels multiply strength. A single-width bridge carries light vehicles. Add identical panels side by side, and you double the load capacity. Stack panels vertically and you triple it. The same basic component, combined in different configurations, could create bridges ranging from light infantry crossings to heavy tank spans. Standardization meeting flexibility. Bailey sketches through his entire commute. By the time the train pulls into Sheffield, he has a complete preliminary design covering 3 notebook pages. That evening, he drafts formal specifications at his kitchen table. Total design time from initial concept to working drawings. About 6 hours. He submits the proposal to his supervisor September 12, 1940, with a cover note, Portable panel bridge requiring no special equipment or trained personnel. Recommend immediate prototype testing. The Ministry of Supply's reaction surprises Bailey. They don't shelve it. They don't send it through committee review. They authorize prototype construction immediately. Britain is desperate. France has fallen, invasion seems imminent, and conventional bridging takes too long. Bailey's proposal, if it works, could change that equation fundamentally. October 1940. The first prototype panels emerge from a Sheffield fabrication shop. Bailey supervises construction personally, making modifications as metallurgical realities clash with paper designs. The panels are slightly heavier than planned, 591 pounds each, but still manageable by four-man teams. More critically, the interlocking mechanism works flawlessly. Panels slide together with barely a millimeter of clearance. Pins drop through aligned holes effortlessly, and the resulting structure is rigid despite using no welds or bolts. December 1940. Christchurch Experimental Bridging Establishment. The British Army's testing ground for military equipment. Bailey's prototype bridge, a single-lane span measuring 60 feet, sits across a concrete test pit. Army engineers have spent 2 days assembling it using nothing but hand tools and muscle. No cranes. No specialized equipment. Just men, panels, and pins. The test begins with a 3-ton truck. The bridge doesn't even flex. 10-ton lorry. Still solid. They escalate to a Churchill infantry tank weighing 39 tons. Engineers measure deflection with precision instruments. The bridge sags 2.3 inches at center span under full load, well within acceptable limits. When the tank drives off, the bridge returns to its original geometry. No permanent deformation. No structural damage. The observers include Major General Sir Miles Dempsey, who will eventually command British Second Army during D-Day. He watches the tank cross, then asks Bailey a question that seems simple but carries enormous implications. How long to build a 200-foot span? Bailey calculates quickly. A 200-foot bridge requires 20 panels per truss, 2 trusses minimum, plus decking and cross-bracing. With a trained 30-man crew under ideal conditions, maybe 8 hours. Dempsey's response is immediate. Mass-produce these. Immediately, he understands what Bailey has created. This isn't just a portable bridge. It's a weapon that negates Germany's defensive strategy. Every river crossing the Germans destroy, every blown viaduct they assume will delay Allied advance by weeks. All of it becomes irrelevant if you can build replacement bridges in hours. January 1941. The War Office issues contracts to steel fabricators across Britain. The specifications are precise. Each panel must be identical within 3 mm tolerance. Any panel produced in Manchester must interlock perfectly with panels produced in Glasgow. This standardization is critical because Bailey's design assumes components will be mixed and matched in field conditions with no time for custom fitting. Production ramps up slowly at first. Factories are already overloaded making tanks, aircraft, ammunition. Steel is rationed. But as military planners grasp the strategic implications, Bailey bridge production receives priority classification. By mid-1941, 8 factories are producing panels. By 1942, that number reaches 15. Peak production in 1944 hits 25,000 panels monthly, enough to build 40 complete bridges every 30 days. But production is only half the challenge. The other half is training. Bailey's design is simple, but simple doesn't mean obvious. Soldiers need to understand panel orientation, proper pinning sequences, load distribution principles. The War Office establishes Bailey Bridge schools at training facilities throughout Britain. Every engineer regiment receives a specialized platoon trained specifically in rapid bridge construction. The training emphasizes speed. A peacetime bridge might take careful deliberation, multiple safety checks, conservative timelines. Combat bridges require different thinking. You build under artillery fire. You build at night without lights. You build while enemy snipers are targeting your crew. The training exercises replicate these conditions: smoke grenades obscuring vision, instructors shouting simulated artillery warnings, arbitrary time limits forcing rush decisions. March 1942. Tunisia. The first combat deployment of Bailey bridges occurs during Allied operations in North Africa. British forces advancing inland encounter a blown railroad bridge over a wadi, a dry riverbed that becomes a raging torrent during rainstorms. The German demolition team did thorough work. The original bridge is twisted wreckage scattered 100 meters downstream. A Royal Engineer Company arrives with Bailey panels loaded on standard lorries. They've practiced this exact scenario 50 times in training. The reality is messier. The approach banks are unstable. The riverbed isn't level. Enemy patrols probe their perimeter throughout the night. But 14 hours after starting, they have a functional 80-foot bridge capable of handling medium tanks. Rommel's forces, expecting the wadi to be impassable for at least a week, find British armor crossing the following morning. The Tunisia success triggers immediate demand from every Allied theater. American forces request thousands of panels for the Pacific. Soviet liaison officers ask about licensing the design. Free French engineers want training teams. Bailey's simple panel system has become the most requested piece of military equipment that isn't a weapon. But North Africa also reveals limitations. The single-width Bailey bridge carries tanks, but barely. A Churchill at 39 tons is near the design's maximum capacity. American Sherman tanks at 33 tons have comfortable margin. But the new British Comet tank under development will weigh 44 tons. The next generation American Pershing will exceed 45 tons. Bailey's design needs scaling up. The beauty of the modular system is that scaling is simple conceptually, just add more panels. A double-width bridge uses 2 panels side by side, connected by horizontal stringers. A triple-width uses 3. Vertical stacking works similarly. Add another layer of panels above the first, pinning them together through aligned holes. A double-single bridge, 2 panels wide, 1 panel high, can handle 60 tons. A triple-double, 3 wide, 2 high, handles over 100 tons. But there's a catch. The structural math gets complicated fast. Bailey had designed the connections to handle specific load distributions. Adding panels changes how forces propagate through the structure. Do the connections still work at triple-double configuration? Will the pins shear under concentrated loads? What about lateral stability when wind hits a bridge carrying a 40-ton tank? Bailey spends 6 months in 1942 conducting structural analysis. He builds scaled models, runs load tests, calculates stress distributions by hand using slide rules. Modern engineers would use computer finite element analysis. Bailey has pencil, paper, and mechanical calculators. He verifies that a triple-double configuration maintains adequate safety margins under worst-case loading. The connections, somewhat overbuilt in the original design, have enough capacity to handle the multiplied forces. July 1943. Sicily invasion. This is where Bailey bridges face their toughest test yet. Combat assembly under direct fire. German forces are conducting fighting retreats, destroying every bridge as they withdraw. Allied engineers are racing behind them, throwing up Bailey spans before German artillery can bracket their position. The bridge at the Samito River becomes legendary. German demolitions destroyed a 200-foot railroad bridge that was the only viable crossing for 30 miles. British XXX core tanks are stacking up on the southern bank while German forces dig in on the northern heights. Every hour of delay lets the Germans strengthen their defensive positions. The Royal Engineers 7th Field Company gets the mission. They arrive with enough panels for a triple-double configuration, the heaviest Bailey variant yet attempted in combat. The assembly site is under observation from German positions. Smoke shells provide concealment, but smoke drifts and artillery fire walks through the construction area every 10 minutes. They work in organized chaos. 4-man teams carry panels from staging areas to the bridge approach. Assembly crews swing each panel into position, align the pinholes, drive pins with sledgehammers. The rhythm is mesmerizing. Lift, position, pin, repeat. German shells explode close enough to throw mud onto the workers, but the work doesn't stop. Casualties are evacuated, replacement teams step in. The bridge grows steadily across the gap point 14 hours after starting. The bridge is complete. The first tank across is a Sherman from the Canadian 1st Division. The commander reports the bridge feels solid as London Bridge. XXX Corps pours across, overwhelming German positions that assumed they had days to prepare before British armor arrived. The Samido crossing becomes a case study in what rapid bridging can achieve tactically. September 1943. Planning for Operation Overlord, the invasion of Normandy, begins in earnest. Allied logistics officers face a problem that makes everything in North Africa and Italy look simple. They're planning to land 150,000 men in the first 48 hours. Those men will need continuous supply, fuel, ammunition, food, replacements. The supplies will come through the beaches, but they need to move inland quickly to avoid creating bottlenecks that German artillery will destroy. Normandy's geography is deliberately difficult. The hedgerows create natural defensive positions. The rivers, the Vire, the Orne, the Douve, crisscross the invasion zone. German defensive doctrine assumes these rivers will channel Allied movements into kill zones. Every permanent bridge has already been pre-wired with demolitions. The moment Allied forces land, German engineers will blow every span within 50 miles of the coast. The logistics calculations are brutal. If bridge construction takes traditional timelines, 3 to 5 days per span, the invasion will stall within a week. Allied forces will be compressed into beachheads while German reinforcements arrive and counterattack. But if Bailey bridges can go up in hours, the entire defensive calculation changes. Rivers stop being barriers and become mere inconveniences. The planners stockpile Bailey components in Britain throughout late 1943 and early 1944. Warehouses fill with steel panels. Every invasion convoy includes ships loaded with nothing but bridging equipment. The numbers are staggering. 700 complete bridge sets ready for transport. That's enough panel stock to bridge every major river in Normandy twice over, with reserves remaining. Training intensifies. Royal Engineer regiments practice speed construction competitions. Which company can assemble a 100-foot span fastest? The record falls repeatedly. By May 1944, elite teams are completing single-width bridges in under 4 hours. American engineer battalions train alongside British units, learning techniques developed through 2 years of combat experience. June 6, 1944. D-Day. The first 24 hours go reasonably according to plan, reasonably meaning casualties are horrific but beachheads are secured. As predicted, German engineers detonate every bridge within 20 miles of the coast. Reconnaissance reports 63 destroyed crossings requiring immediate replacement. The race begins. The first Bailey Bridge in France goes up over the River Soules near Cruilly on June 7th, barely 30 hours after the initial landing. Royal Engineers from 17th Field Company work through the night while German snipers harass them from hedgerows 300 meters away. They lose 2 men killed and 5 wounded, but the bridge stands. British tanks from the 7th Armored Division cross at dawn, advancing inland while German forces are still repositioning to block what they assumed would be an impassable river. The pattern repeats across Normandy. Engineers arrive at destroyed crossings, assess the gap, calculate required configuration, and start building. Most bridges are single or double width, fast to construct, adequate for supply trucks and light armor. Critical crossings get triple-double configurations that take longer but can handle the heaviest tanks. By June 12th, Allied engineers have installed 84 Bailey bridges. By June 20th, that number reaches 200. The German defensive strategy, predicated on using destroyed infrastructure to channel and delay Allied advances, collapses. Everywhere German commanders expect delays, British and American forces simply bridge the gap and keep coming. Field Marshal Montgomery later writes in his memoirs, "The Bailey Bridge was the single most important piece of military equipment deployed in Europe. Without it, the breakout from Normandy would have been impossible." August 1944. The breakout from Normandy accelerates into a pursuit across France. German forces are retreating faster than Allied planners anticipated. This creates a new problem. Supply lines stretching hundreds of miles need constant maintenance. Every retreating German engineer unit destroys every bridge they cross. The Allied advance becomes a race between combat units moving forward and engineer units building bridges to keep them supplied. The Bailey Bridge's modularity proves invaluable in unexpected ways. Standard bridges are built to specific lengths. You calculate the gap, design accordingly, build once. But combat conditions are never standard. A gap measured at 80 feet might actually be 85 feet when you account for unstable approach banks. A bridge designed for 100 feet might only need to span 90 feet if you can cantilever from stable rock outcroppings. Bailey's pin and panel system handles this variation effortlessly. Too short. Add panels. Too long. Remove panels. The adjustment takes minutes, not days of redesign. Engineers develop improvisational skills that would horrify peacetime bridge designers. Cantilevering spans beyond recommended limits, using damaged panels in non-critical positions, mixing panel vintages from different manufacturers. September 1944. The Rhine River looms ahead. This isn't a tactical obstacle like Norman streams, it's a strategic barrier. The Rhine averages 400 meters wide, fast-flowing, with unstable banks. German propaganda calls it impregnable. Every permanent bridge has been demolished. German generals assume the Rhine will hold Allied forces until spring 1945 at earliest, when massive bridging equipment can be brought forward. But Allied engineers aren't planning massive bridges. They're planning multiple Bailey bridges at different crossing points, overwhelming German defenses through quantity rather than monumentality. The longest Bailey bridge ever attempted will span only 210 feet. Small by Rhine standards, but you don't need to bridge the entire river. You need to bridge from the west bank to sandbars and islands, then island hop to the east bank. March 23, 1945. Operation Plunder, the Rhine crossing. British XXX Corps and U.S. 9th Army launch simultaneous assaults at multiple points. The German defenders fight desperately, but they're defending a line that assumes bridge construction takes weeks. Instead, Allied engineers have Bailey spans going up within hours of securing bridgeheads. The crossing at Xanten becomes the showcase operation. Royal Engineers from the 15th Scottish Division reach the East Bank at 0430 hours on March 24. German forces are still reeling from the initial assault when Bailey panels start arriving on dukus, amphibious trucks that ferry components across the river. By 1200 hours, a single-width Bailey span connects the west bank to a sandbar 110 feet offshore. By 1600 hours, a second span jumps from the sandbar to the east bank. Total time from securing the crossing to operational bridge, 11 hours and 30 minutes. General Eisenhower visits the site March 26 and walks across personally, accompanied by reporters and cameras. The symbolic importance is immense. The Rhine, Germany's last natural defense, breached by a portable bridge built faster than most people could believe possible. But not every crossing goes smoothly. At Wesel, German artillery zeroes in on a Bailey bridge under construction. The first salvo kills 6 engineers and destroys 12 panels. The crew evacuates, waits for counter-battery fire to suppress the German guns, then returns and continues building. The second salvo hits again, killing 4 more men and damaging the partially assembled span. They rebuild the damaged section and finish the bridge. 18 men died building a crossing that German commanders assumed was logistically impossible. The final statistics for Europe are staggering. Between D-Day and VE Day, Allied forces constructed over 4,500 Bailey bridges across Western Europe. That's an average of 12 bridges per day every day for 11 months. Some were small 30-foot spans over farm streams. Others were engineering marvels, 200-foot triple-double configurations carrying hundreds of tons daily. The bridges weren't just tactical tools. They became strategic infrastructure. Many Bailey spans remained in place for months after the war, carrying civilian traffic while permanent bridges were rebuilt. Some stayed operational for years. In 1950, several Bailey bridges built during the 1944 advance through France were still carrying commercial traffic. The temporary bridge designed for combat use proved durable enough for peacetime civilian service. But the war also exposed Bailey bridge limitations. The heaviest variant, triple-triple configuration with 3 panels wide and 3 high, could theoretically handle 120 tons, but assembly required enormous effort and time. Each additional layer of complexity multiplied construction difficulty exponentially. A single-width bridge might take 4 hours. A triple-triple could take 40 hours and require 200 men working in coordinated teams. military engineers started requesting improvements. Heavier panels that could carry more load without multi-layer stacking. Improved connections that required fewer pins. Pre-assembled sections that could be lifted by crane instead of hand-carried. Bailey's original design was brilliant for 1940 technology, but by 1945 expectations had evolved. Donald Bailey, knighted in 1946 for his contribution to victory, returned to civilian engineering. He designed improved versions through the 1950s. The medium girder bridge used lighter aluminum alloys. The heavy girder bridge incorporated prefabrication concepts. But these variants never achieved the iconic status of the original Bailey bridge. Sometimes simplicity is genius, and improving it makes it less elegant rather than more useful. The Korean War in 1950 proved the Bailey design's enduring relevance. American forces found themselves fighting in terrain where infrastructure barely existed. Mountain roads connecting villages, small bridges spanning ravines. North Korean and Chinese forces destroyed every crossing during retreats. U.S. Army engineers, many of them World War II veterans who'd built Bailey bridges in Europe, found themselves doing it again in Korea. The Korean experience refined construction techniques further. Engineers developed specialized equipment for difficult terrain, portable winches for pulling panels up steep slopes, lightweight decking that reduced total bridge weight without sacrificing strength, rapid assembly kits pre-organized for specific configurations. A Bailey bridge in Korea in 1952 could be assembled 30% faster than the same bridge in France in 1944, not because the panels changed, but because techniques evolved. Vietnam saw limited Bailey bridge use. The guerrilla nature of that conflict didn't involve conventional advances across destroyed infrastructure. But the bridges appeared in unexpected contexts. U.S. Army engineers used Bailey panels to create floating bridges across rivers by mounting them on pontoons. They created temporary airfield overruns by laying panels across soft ground. The modular system's flexibility allowed applications Bailey never imagined when sketching on that train in 1940. The Cold War maintained large Bailey bridge stockpiles. NATO doctrine assumed Soviet forces would destroy hundreds of bridges during any European conflict. Prepositioned bridge sets sat in warehouses across West Germany, ready for deployment. Training exercises practiced speed construction. British and American engineers competing to see which unit could build fastest under simulated combat conditions. The bridges never deployed in anger during the Cold War, but their existence shaped strategic planning on both sides. Modern military forces still use Bailey bridge descendants. The British Army's medium girder bridge, introduced in 1971, is recognizable as Bailey's conceptual air, modular panels, pin connections, hand assembly capability. The U.S. Army's dry support bridge system uses similar principles with updated materials. NATO maintains compatibility standards ensuring different nations' bridge systems can interconnect during coalition operations, a direct descendant of Bailey's insistence on standardized panels. But the most surprising legacy is civilian disaster relief. When earthquakes, floods, or tsunamis destroy infrastructure, Bailey-type bridges appear within days. International relief organizations stockpile modern variants specifically for emergency deployment. The same characteristics that made them effective in combat, rapid assembly, no special equipment required, adaptability to varying conditions, make them ideal for disaster response. December 2004. The Indian Ocean tsunami devastates coastal infrastructure across multiple countries. Roads and bridges connecting interior regions to coastal areas are destroyed. Relief supplies stack up inland while survivors on the coast lack food, water, and medical care. Within 72 hours, military engineer units from multiple nations arrive with Bailey-type bridge components. Within a week, temporary spans reconnect interior supply routes to devastated coastal zones. Haiti earthquake, 2010. Japan tsunami, 2011. Nepal earthquake, 2015. Pakistan floods, 2022. Every major disaster sees Bailey bridge variants deployed. The technology is now 80+ years old, but it remains relevant because the core engineering insight, modular standardization enabling rapid deployment, transcends specific materials or manufacturing techniques. Contemporary bridge designs incorporate Bailey's lessons in unexpected ways. Modular pedestrian bridges use similar interlocking concepts. Emergency vehicle bridges for fire departments employ pin connection systems allowing rapid deployment. Even children's construction toys like Meccano and KNEX reflect Bailey's insight that simple standardized components enable complex structures. Donald Bailey died in 1985 at age 83. His obituaries focused on the Bailey Bridge, sometimes mentioning other civil engineering work, but always returning to those panels sketched on a train. He'd spent 4 decades after World War II designing various projects: buildings, permanent bridges, industrial structures, but nothing else achieved remotely comparable impact. In interviews late in life, Bailey expressed surprise at his creation's enduring relevance. He'd assumed the design would become obsolete within a decade as materials and construction techniques evolved. Instead, the concept proved timeless. When asked to explain the Bailey Bridge's success, he consistently downplayed his role. "I just applied simple engineering principles to a practical problem. Any competent engineer could have done the same." But that's demonstrably false. Thousands of competent engineers had wrestled with portable bridge design before Bailey. They'd produced complicated systems requiring specialized equipment, extensive training, lengthy assembly times. Bailey's genius was recognizing that the problem wasn't lack of engineering sophistication, it was too much sophistication. The solution wasn't more complexity, it was elegant simplicity. The panels don't require welding, so you don't need specialized welders. They don't require cranes, so you don't need heavy equipment. They don't require precise ground preparation, so you don't need extensive site work. Every requirement removed is another potential failure point eliminated. By the time Bailey finished stripping away unnecessary complexity, he'd created a system so simple that exhausted soldiers under enemy fire could build it correctly. Military historians argue about which weapons or tactics were most decisive in World War II. Tanks, aircraft, radar, code-breaking, all legitimate candidates. But logistics determines whether tactical brilliance can be sustained. You can win every battle and still lose the war if you can't supply your forces. Bailey bridges weren't glamorous. They didn't kill enemies or blow up installations. They just kept armies moving when movement should have been impossible. The strategic impact becomes clear when you examine what Germany expected versus what actually happened. German defensive doctrine throughout 1944 to 1945 assumed destroyed infrastructure would delay Allied advances by weeks per major obstacle. Blow a bridge over a significant river, and enemy forces stopped for 10 to 14 days minimum while engineers construct replacements. Multiply that across dozens of rivers between Normandy and Berlin, and you've bought months of time to regroup, reinforce, and counterattack. Instead, Allied forces bridged obstacles in hours to days. The expected delays never materialized. German generals would order demolitions, receive confirmation the bridges were destroyed, and then receive panicked reports 18 hours later that Allied armor was already across. The psychological impact was devastating. If you can't slow your enemy by destroying infrastructure, you have no coherent defensive strategy. Post-war analysis by German officers reveals consistent shock at Allied bridging speed. General Hans Speidel, Rommel's chief of staff, wrote in 1949, "We could not understand how the Allies built bridges faster than we could destroy them. Our intelligence reported no special heavy equipment, no revolutionary construction methods. Yet bridges appeared overnight. This capability, more than air superiority or numerical advantage, made sustained defense impossible." The Bailey Bridge also changed post-war thinking about military engineering. Before World War II, armies treated bridging as specialized task requiring expert units with extensive equipment. After World War II, every army adopted modular bridge systems that ordinary soldiers could assemble. The democratization of complex engineering, making sophisticated capabilities accessible to non-specialists, became standard military doctrine. Modern modularity concepts across all industries trace lineage partially to Bailey's insight. Shipping containers revolutionized global trade by standardizing cargo dimensions. Modular construction revolutionizes building by standardizing wall and floor panels. Data centers revolutionize computing by standardizing server racks. The underlying principle, standardized components enabling flexible systems, echoes Bailey's train commute sketch. Physical examples of Bailey's original bridges still exist. The Bailey Bridge Museum at Fort Leonard Wood, Missouri, maintains operational sections demonstrating World War II-era construction techniques. Several bridges built during World War II remain in service. The Kelowna Floating Bridge in British Columbia incorporates Bailey panels in its structure. Burma's infrastructure includes multiple Bailey bridges from the World War II Burma campaign, still carrying traffic 80 years later. The engineering community recognizes Bailey's achievement. The Institution of Civil Engineers in Britain awards the Sir Donald Bailey Medal annually to engineers demonstrating innovation under resource constraints, honoring the spirit of solving complex problems with simple solutions. Military engineer training worldwide includes Bailey bridge construction as fundamental skill, taught alongside map reading and demolitions. Donald Bailey never sought fame or fortune from his creation. He held the patent, but when the British government requisitioned it for wartime production, he accepted minimal compensation. After the war, when other countries manufactured Bailey bridges without licensing, he didn't pursue legal action. His attitude was pragmatic. If it helps people, use it. There's profound lesson in Bailey's story about how innovation actually happens. Military contracts, massive budgets, teams of specialists. None of that produced the solution. Instead, a single mid-level engineer thinking during his morning commute sketched something simple that worked. Not because he was uniquely brilliant, but because he asked different questions than everyone else was asking. The Bailey Bridge succeeded because it prioritized the right constraints. Not how do we make the strongest bridge, but how do we make a bridge 4 men can carry? Not how do we optimize load capacity, but how do we assemble without cranes? Every design decision favored deployability over performance, simplicity over sophistication. That train commute in September 1940 produced technology that helped win the largest war in human history, prevented countless deaths by enabling rapid disaster response, and established engineering principles still taught today. A notebook sketch became 700 bridges built in 48 hours during D-Day. An envelope doodle became the logistical backbone that kept Allied armies advancing when they should have stalled. Sometimes the most revolutionary innovation isn't complex new technology. Sometimes it's recognizing that the complex technology everyone's developing is solving the wrong problem. Sometimes genius is simplicity that actually works instead of sophistication that theoretically should. The Bailey Bridge. 10-foot panels, 591 pounds each, connected by steel pins. Simple enough for 4 men to carry, robust enough to carry 40-ton tanks. Designed in 6 hours, proven in 4 years of combat, still relevant 8 decades later. That's engineering that changed warfare by understanding that sometimes less is more, and simple is the hardest thing to get right.